can perhaps be the greatest technology to improve the quality of our life. So first, robotics started in factories like this, right? 3 decades ago, where you have the robot welding a car. There's a gate, human outside. When the gate opens, the robot shuts down. I call this the structured environments where there is human-robot separation. Because when human comes in, the robot doesn't know human went in. The robot will just do. You don't want the robot to weld the human part, right? Right? So we get them out of the picture. It has been very effective. It works up to today, but the applications of robotics is much more than that, outside the factory to our daily lives. So what is needed, right? And we're starting to see that. That's why I say we're at a moment of great opportunities. These are more recent applications of robotics. The robot is worn, it's a wearable robotics, by a company called Hybrid Assist Slim. The company is called Hybrid Assist Slim. The company is Cyberdyne from Japan. You wear it so you don't get tired walking. You can carry heavier things, right? Many applications. For example, first application in military for soldiers carrying, typical heavy backpacks for their equipment so they don't get tired. The robot is inside the human body with 2 pinchers grabbing a human organ, a soft organ, operated by the doctor using 2 joysticks. If you're good in playing games, you will be good in doing this. Right? And you see what the robot is doing through a camera there, right? Then you can open and close. This is the Da Vinci robot from Intuitive Surgical. I met a doctor in Singapore, first hospital in Singapore to use it. He doesn't like it. He's a heart surgeon because he says it's like you're having Chinese dinner with chopsticks that is 1 meter long. Right? You're gonna eat, right? Then how do you manipulate that? But of course, the advantage is minimally invasive. You have 3 holes in your body: 1 hole for the left arm, 1 hole for the right arm, another hole for the camera, and you do the task of cutting, slicing, and doing the heart bypass surgery. It was designed for heart bypass, but today the most use of it is for prostate surgery, which is quite interesting too. So that's the robot is inside the human body, robot around the human body. The robot vacuum cleaner, Roomba, perhaps the only consumer level robotics that has sort of went to our daily lives, cleaning our homes. The robot inside your home, you're inside the robot in a robotic car, and you're interacting with the robot. Real application is really companionship. And when you're older, so the robot not only giving you assistance of daily living for physical activities, but also as a social companionship. I don't think anything wrong with that. And that can also be your advanced mobile phone to talk to your loved ones, right? It can run Skype, it can run Zoom. And if you provide force feedback in all of this, maybe pretty soon you're talking to a robotic phone and your loved one from across the globe can actually move the robot and touch you, and you can feel the warmth. You can even have a remote relationship, a remote kiss maybe, something like that. It's quite exciting. Yeah, so what is the commonalities about all of this as compared to this? It's really the human-centered nature, where the impact of robotics is really not separating it from humans, but making it the best tool to help humanity. Right? So we want to go from this in structured human-robot separation to let robots work in such environment in the grocery aisles, right? For example, doing stock replenishment, a truly manless grocery, or a shopping center where the environment is unstructured and there is human-robot interaction. So the question is, how do we move from an environment designed for the robot to an environment designed for humans, which ought to be, and the robot is intelligent enough to operate in that environment without modifying the environment. That's why our work on self-driving vehicles, we make the intelligence egocentric. It's all within the robot itself. It doesn't rely on GPS. It doesn't rely on lines on the floor to guide it. It doesn't rely on barcodes to guide it. Right? Of course, if it's there, we can use it, but we don't rely on it. So how do we get there, right? How do we get human-centered collaborative robots where the robot is really the ultimate tool, perhaps the best tool to serve humanity? Yeah? We want to answer these 2 important questions. What is the right level of autonomy, and how do we collaborate, right? Of course, we want the best autonomy. The more autonomous, the less we need to do. the better is our quality of life. So if you look at the spectrum of tasks here, the top graph, simple tasks to more complex tasks, maybe somewhere here would be, for example, a washing machine as an intelligent system. What does the human need to do for a washing machine? The machine is doing most of the stuff. The human perhaps just does the setting, right? Whether the time for washing, whether it's mild, or what kind of level of washing you want, and pushes a button, the machine does the washing. Right? That's perhaps somewhere here. A more complicated task today is driving a vehicle. Can a robot drive a vehicle today? It's a very complex task. The machine is quite stupid, but there's some autonomy in the machine, like driver assistance system, like lane following, adaptive cruise control, maintaining the distance of front vehicle, but the human's still in charge. So human does more and more. That's a very complex task, right? But as we work in technology, we want to really do this arrow to move, to improve the machine intelligence, to make the human does less and less, so human does more meaningful jobs. And at the same time, as humans does more meaningful jobs, or does less, our human nature is such that we always want to have more. So then we'll have more expectations. Perhaps in the washing machine example, right? A future washing machine, right? You don't need even to press a button. The clothes from your closet goes to the washing machine, and after that, after it's washed, it gets ironed and put back to your closet, right? Perhaps something like that. Of course, in self-driving vehicle, we want it to be, you call Uber or Grab, the car comes to you. Literally, there's no driver there. You just say where you want to go. And Singapore is working very hard to have that. In 2022, they already announced it, to have a driverless bus system as a public transportation in 3 areas in Singapore, 3 districts in Singapore, including this area, which is the Dover Road, One North, Buena Vista, Holland Village area, and NUS. So we want to move here. So it's always never ending, and that's what makes technology fun, right? We're always chasing upon a bar that gets go higher and higher. As the bar gets higher, life improves, right? So, robots as tools, what does the tool mean? It doesn't operate by itself, really. So people always worry, will robots take away our jobs? Well, it's true, they will take away our jobs, but if they do take away our jobs, they ought to take away those jobs. Because those jobs are so boring, dangerous, right? It's too... Humans are too intelligent to be doing such mundane tasks. And working in a structured environment, right, where unstructured means you don't know where things are. The robot must be intelligent enough to know where things are and to manipulate them. And why it's unstructured? Because it's first structured, it becomes unstructured because a human being, you will know that when you move to a new house. You move to a new house, it's very nice. When you move to a new house and move to a new office, it's very nice. After a month, it gets a bit messy. If you go to my office, you'll know how messy it is. And why? Because people move in here, right? And people are in general disorganized. So how do we move towards robots must be intelligent enough to adapt to the environment rather than changing the environment, adapting to the robot. So that's the whole global sort of holy grail of robotics in getting robots out of the factory to everyday life, like in this room here, right? So these are industrial robot designs. To make it human-friendly, this is what it is today, right? This is bought by KUKA. Industrial robot, a collaborative robot by KUKA. What's the difference between these two? Is sexiness, right? Smoothness, right? I think this is smooth, you can touch it. This is kind of rough. But besides appearance, one important difference is this robot, the joints have force sensing. While this robot does not have, it only has motion and velocity and position sensing, right? Compared it to the human body, when I'm walking here, I can walk. Am I doing motion control? Yes. Am I doing force control? Yes. I'm doing both, right? Can you imagine walking without feeling your legs? I think you cannot walk, right? When we do tasks, we feel our joints. So that's the first step. How do we give robots the sensation of feeling when it's moving? And this robot has this, that's why they call it a collaborative robot. So precision motion control is not enough. You need to have force control, feel the joints, but at the same time, you don't need the motion control to be exact. Many people work on robotics, they say, I want to make a super accurate robot. if the robot is very accurate, it can work in an unstructured environment. I don't agree with that because even if it's super accurate, the environment is not structured. It's not accurate, so there's no point doing that. The human body is a classic example. We're not accurate in our motion, but we can do many tasks that robots cannot do because we regulate also the forces and motion together, right? Something we call compliant motion. Secondly, we need new design of robots. We don't want robots like this or even like this to be living with us at home, right? It would be nice if the robot is something like Hero, Big Hero, or Baymax, a bubbly balloon type robot that you won't be afraid of it. You can even embrace it. It's like cushioning, right? So we need new design of robots. Most robots have motors like this too, but perhaps our human body, we don't have motors, we have muscles, right? So why is it like that, right? And besides the design, the hardware improvements, we need also improvements in the intelligence, right? Different levels of intelligence. So the following slide shows some of our work in those aspects. First, the hardware, mechanical intelligence. This is a work of what people call soft robotics, where you have fingers that are made of silicon with thread embedded in it. The thread provides a skeleton, right? By pumping air into it, it will change its shape, it will coil to grasp an object. And it's mechanical, so it always does the same thing. The only difference is the air pressure, right? The more air pressure it is, the higher the pressure, the more coily it gets, right? The same idea, using fingers that are 3D printed, using some kind of thermoplastic urethane rubber type material that we 3D print with air channels embedded in it, in such that the print pattern of the structure, the air channels is such that when you pump air, it will move in the correct mechanical way without active control. The control is turning on and off the valve. The same thing on using pouches, air pouches. By selectively powering the air pouches, you can have small little joints or fingers that move together to grasp a balloon, for example. So these are inherently safe. These are fingers, but can we make an arm made of this? Can we make a whole robot like this, right, to be human-friendly? So that's some of the work we're doing. You can achieve soft robotics in a different way. This is 3M's very high bonding tape. The same double-sided tape, when you peel off the backing and you somehow compress it or stretch it in area-wise so the thickness reduces, apply a voltage across it. Once you apply a voltage, the area expands further. Turn off the voltage, the area shrinks, right? And you can see it here. The idea is, how can you take advantage of this physical phenomena? You apply power, it expands, turn off the power, it shrinks. It's like a rubber band, you pull and let go, it goes back. Can you do something meaningful with it? So this is like an intro mechanism. First time we saw this, what does this remind you? There's something in our body, you put electrical charges, it contracts or extends and turn off. These are muscles, right? So can we have this as artificial muscles? And in the world, there's a competition for arm wrestling against a human using electroactive polymers. Right? So it's interesting. So why is it black? Right? Because we paint carbon grease on it so that the charges are spread easily. It's a bit messy, but we can also use the same, I forget what it's called, when you go for ultrasound, let's say your wife is pregnant, and you don't have a wife yet. So anyway, but let's say to that gel type thing. And so the same material can be used. Motors can also operate as generators. So the same thing, if you don't apply voltage, you apply mechanical motion, it generates charges. So this can be an energy harvesting device. A dream is, can we put this under the roads, under the humps, and perhaps cars going can power all the traffic lights and lampposts in the world to have really zero energy life to be sustainable, right? Off-the-shelf product, very high bonding tape. I met 3M people, they even don't need some of them. The person I met don't even know this use of it. Right? So they're very excited about it. The only negative thing you might think is, guess how much voltage is applied to this? Can anybody? DC, how much? Give a guess, it's very high. Anybody? 120 volts? No. It's actually 10,000 volts. 10,000 volts DC, but very, very low current. We have demonstrated that powered by AA battery, AAA batteries. So it's very low current. There's actually practically no current. Mobility is very important. We need a robot not only to be able to manipulate, but also to move, like a human, like move. I think the best mobility is our swivel chair, right? this is the, next time you see a swivel chair, look under it. There's an offset between this axis and this axis, the center. And this offset, ideally, is the radius of the wheel, which is very interesting. It must be equal to the radius, so it's equal effort in going X and Y. Yeah? You don't want a chair that is harder to push this way compared to that way. So can I put one electric motor here, one electric motor here? These are the two motors. And by powering the four motors in this case, these two are swivel casters, you can get omnidirectional motion, right? Can you imagine if our cars have this kind of wheels? Then when you want to do parallel parking, you can just do like this, right? It's very interesting. With the offset equal to the radius of the wheel, it's very efficient. So it's nice. So we're building a manipulator on top of this, perhaps a human-friendly robotic manipulator to be running around in our home, in everyday life, helping us in our daily tasks. So that's our grand vision. I talk about force control. These are different ways that we have programmed it. We can program something to appear like a spring, or we can make it very stiff like position, or very soft like a force. When this is going up, it touches a paper, an A4 sheet of paper, and then it stops. So it's that sensitive, and we can control the stiffness, right? So in addition to having a material that is inherently soft, rubbery, we can have control algorithms on top of that, using a mechanically stiff robot through control to make it not stiff and to program the mass properties. Right? And we have applied that to things like this. For example, tasks like this. I call this reflex action, the lowest form of intelligence where it reacts according to forces without thinking. It's almost like when you touch a hot object, when you cook, you don't think, you just quickly do this, right? I suppose you don't think, but we cannot really have an experiment to test that, right? Because the only way is to cut your head off and put your arm on a hot object, right? But I think there is some evidence, like even animals, you cut a chicken's head, the chicken still runs around for less than a minute, right? How does it run? It requires high-level control, right? So it's doing some kind of reflex action. So we like to have the robot to do that too. Something like the previous slide, impedance control, controlling the compliant motion. And we can do tasks like this without vision, just from feeling the joints. All it needs is the power of feeling the joints. Can you do tasks like this? In this case, it's polishing an aircraft canopy, and it's just doing this blind. And Rodrigo, my student, is moving the base. The robot doesn't know the base is being moved. All the robot does is just does this back and forth, applying a very small 10 Newton force in this case, while it's doing polishing. Right? And here, this is a more recent work, a very sharp discontinuity. The robot is also able to overcome this without vibration. This is very hard for a robot to do. And we have applied that to deburring applications. This is work with the Singapore Institute of Manufacturing. Deburring application, removing the burr, where this is now behaving like a spring. This is a small robot carried by a big robot. One of the robots that I showed you in the earlier slide, the orange robot. We call it a macro mini, a big robot that is not sensitive, carrying a small robot that has fine motion capability and force control, combining the big workspace of the big robot to the fine manipulation capability of the small robot. So these are the burrs we're trying to remove to create a very good finish of an aircraft engine part. Here we're applying a force of 2 newtons, very small force. It's very hard, it's impossible to use a robot today. But this is just an experimental system. So I want to go higher now to the higher form of intelligence, higher level of intelligence. And besides reflex action, these are the 4 things that human beings do, right? And machines need to do this first. First, sensing, using sensors, perhaps a camera, or a rangefinder, or a LiDAR for autonomous vehicles. From the sensors, raw data, you need to create meaning. For example, if the vision system sees the road, I know this is a pothole, I shouldn't go under it, or over it. I know this is a classroom, right? I know that's a chair, I shouldn't stand on it. How to create situational and context awareness. That's very interesting, very important. Robots are not so good at that. After you understand the environment through the sensing and perception, you plan what to do. And after you plan what to do, you actually do it, you execute it. And after you execute, you learn, did you do well in executing it? Did you do well in planning it? Did you do well in sensing it? So there's always a feedback, and that feedback will change how you sense next time, will change how you plan next time, will change how you execute, and this does forever, right? A child learning how to walk for the first time, and as you walk and walk more, you get better and better. So we're doing this every day, right? All the time. Right? Can we put this intelligence into our machine? There are two basic approaches to do that. The first approach is model-driven. We study engineering and science based on model-driven approach. We create a model of the physical world. This is a mathematical equation. Given input, it creates an output. If you have a mathematical description of the world, if you want a desired output, you can use the model to compute the required input to create the desired output. Very easy, if everything can be modeled, right? But you know the model is never accurate. So because of that, we need feedback. Otherwise, it will be purely open loop. Feedback, maybe your output is not quite the desired output, so you use that feedback to change the input so that even if your model is not accurate, it can still work. So that's why we study science, right, to create a model. But as you know, many things you cannot model, right? For example, modeling a human being, even modeling a relationship, your wife or your partner, your loved one, your mother, father, right? If this is a mathematical model, you want to ask money from your mom and dad, that's your output, what input should you give, right? So if you have a mathematical model, you know what input, then you get the money, right? Obviously that doesn't work. So what you do, you try a few techniques. If it doesn't work, you keep trying and trying, you will learn, right? So certainly many things in life is not really scientifically model driven. And that has become a bottleneck over the past several years. That's why advances of robots in outside factories have been limited. But come to the rescue, now today, there are many data-driven approaches. This is accelerated by the availability of better hardware. For example, NVIDIA. You all know NVIDIA because you play games. The same games for your graphics card, right, can be used to simulate a neural network, brain cells operating in parallel with the brain. And how it learns is learning from experience, which is data. It's like you want money from your mom or dad, from experience, you know what works and what doesn't work, right? So we need advances in computing hardware. We need also lots of data to learn. And in the last 2 decades, this has accelerated because of the internet. All of us have Google accounts, right? Now, why does Google, Microsoft give you free accounts? Because you have accepted the terms and conditions. Your photos are all being examined. Your website, so next time you go to a search engine, right, you type a keyword, you use my computer and your computer, what comes out is different. Same keyword. Why? Because it's customized. In the last decades, availability of data, availability of computing power, this has made model-driven approaches a reality in the sense that the model is no longer a scientific based on Newton's law, but based on data. The question is which to use, which is better? My answer there is always both. If we have a model, why not use it? But we know the model it may not be 100% accurate, so we use data-driven approach to improve the model. And for cases where it's very hard to model, forget modeling it, just use data. And humans learn from data, right? The first example of neural networks, data-driven model, teaching a computer how a vision system to distinguish between a cat and dog, or a male and female person. For baby, yeah, you see a person that's male, that's female. Imagine you're a new person in the world, you're an alien come to Earth. You see people around. I'm sure you will know there are two kinds of people, a male and a female. Although you will agree with me, there's sometimes you cannot tell. Right? Yeah, it's getting harder these days. But in general, there are two. You don't need any scientific model for that, right? You just look at the data. That's unsupervised learning. We learn that, and it's an artificial construct. People just say this is called male, this is called female, right? Yeah. But many data-driven approaches are not accurate, which is a fact, right? That's why even humans, right? we cannot detect whether it's a male or female, right? But what's the equivalent of a model-driven approach scientific? And people have studied that to detect cat and dog or male or female persons. You look at features of the face, quantify that features into a set of 50 features, and from these 50 features, this group of values is male, this group of values is female, by collecting feature, analyzing it, creating a model of a male and female. Just by saying that, you know how inaccurate that is. Right? So, neural networks to the rescue. With neural networks, many of the current algorithms in advanced machine vision, AI conferences, they always benchmark the best model-based approaches for perception compared to stupid data-driven approaches. The data-driven beat the model-based approaches, hands down. If you do a Google search as early as 2007, you do a Google search with the keyword "the end of theory," right? You'll see a very interesting article written in 2007 that forget science, forget all about this. We can learn from data, right? So very interesting. So I guess being in the university, it's nice to understand things. Right? Not everything is a black box, but it's just too hard with data-driven approaches. So what is this data-driven approach? It's primitive approximation of the human brain as early as 1960, even earlier. This is Bernard Widrow in Stanford University, adaptive linear element. This is a brain cell. What it does is it accepts inputs from other brain cells, does some kind of aggregation, and depends on a teacher experience from the world, it gets excited or sleeps, it gets dormant. Or you can, now today, you can be half excited, 1/4 excited, and send the excitement out, right? So if you have many of them in a multi-layer thing, architecture, this was popularized in the 1980s by McCullough and Pitts, and using backpropagation learning. It was very exciting in 1990, but it quickly died because of, you need massively amounts of parallel computing, right? But in the 2000s, it got revived again. So, can we use that for this, right? And the following slides give an example for our work in self-driving vehicles. I quickly go through this. The same thing, right? But here in the context of road environments where there are people now execute things like this, right? So we have a few vehicles here. We have 3 vehicles that are meant this, and this for pedestrian environment, another vehicle for road environment. And this is our concept. We call it multi-class autonomous vehicles. Multi-class because we have a buggy, we have a car. So the idea is use Grab or Uber to book a car. I want to go to the nearest train station. We're gonna have dinner tonight in this university town. So you can see the dinner place is just beside here. This is CREATE, another acronym in Singapore, Campus for Research Technology Enterprise, or something like that. You book it, the car goes to you, David gets the car, it goes through a typical campus environment, not on the road. I call this a pedestrian environment. Goes to the nearest roadside, where in the nearest roadside you have a physical car waiting for you to bring you to Kentridge Station or Clementi Station. This is what the sensor sees, what was here earlier. It goes through the building. This is the auditorium where we're going to have the closing reception. Inside the building, so we don't use GPS. Since this is a narrow bridge, we do not overtake. These are some of our lecture theaters. A canteen, Flavors of Utah, goes there. Since you want to go to the nearest train station, let's say Kentridge Station, Scott will be waiting for you. This is DJ, this is Scott. They're named after my first student who worked on it. It's also an acronym. Scott means Shared Computer Operated Transport. DJ means it's like a driverless jockey. Okay. Anyway, it knows that you have booked it, so you go inside the car, waiting for you, and you confirm with a PIN, your booking PIN, and confirm your destination. It looks like the same that you see in a taxi application. And when you say go, I want to go, then it just drives itself, right? So we have bought the car, we didn't build the buggy, we bought the buggy, we modified it, we took away the steering wheel. Notice we took away the steering wheel because having steering wheels is a bad idea because humans try to do funny things to them, right? Unfortunately for cars, there's still a steering wheel. Our Department of Motor Vehicle, or LTA, doesn't allow us to do that. But I'm part of a committee. We have recently released TR68, perhaps the world's technical reference, maybe the world's first, for guidelines for autonomous vehicles. So we are working to what people call level 4 and 5 automation, where there's really no vehicle as a public transportation system. As I said, 2022, we'll have it operating in 3 areas in Singapore. So that's the idea of multi-class vehicles, and this is the route that we have been testing. We are in here, Singapore Poly, this is our university. These are official today, already allowed. If your vehicle passed the road test for AVs, you can operate. 2 years ago, we have 9 vehicles. This is our vehicle. Nutonomy is a startup. I'm very proud of them. That came from my group, the Smart NUS group. It started, they have 6 vehicles. 8 people from our lab went and started this together with my friends in MIT, because it's part of the Singapore MIT Alliance. From 8, it grew to 120 people today, maybe 125. And in 2017, this was formed in 2013, it was bought over by Delphi. This won the really quantifiable success story in terms of money, because they bought the whole company for US $450 million. So all Nutonomy doesn't exist anymore because it was bought over. It becomes a subsidiary or the department of Delphi. They're still operating very aggressively. Now they're 120 people. So they're really working towards driverless taxis that you call in a Grab-like application. They actually operated that in One North for some time with Grab as a membership option. So this next slide shows some of the One North footage of videos, some of the problems we're encountering, like road constructions. Because we don't use GPS, that means we have to drive the vehicle once in an unknown environment. The computer remembers the environment and builds a map. Of course, we cannot rely on the traffic light. We have to recognize it. People who jaywalk. So these are things. This is how we do mapping, right? Very quickly, some of our algorithms that we have modified from existing algorithms to get CM level precision maps in a university environment without GPS. So we drive the vehicle. This is the bridge to Newtown. For those with NUS, you will recognize this. This is a roundabout. This is Temasek Lab Engineering Campus. As we're driving the vehicle manually, the LiDARs builds a map. And one difference is the vehicle has an inertial measurement unit, encoders, so we know how much we have traveled, and we can correct the map as we're building it. Notice the adjustment, right? This is going to architecture, and this is Temasek Labs. Notice it's sort of changing shape a little bit, because unlike humans, the robot is very accurate. It doesn't make mistakes. It remembers everything. So because I'm going straight, but the map doesn't say it's straight, so I correct it. So engineering, this is the former McDonald's. Unfortunately, it disappeared already. The engineering cut is being renovated. So that's how we do it. Mapping. Later vehicles, some of the challenges is predicting human behavior. Is this stupid guy not going to move? I'm the one who's going to move, right? But in case the person changes the mind, I will give a safety margin when I try to go around. So it's thinking a little bit and it goes around. We have demonstrated this in hospitals too. A use case with wheelchairs. Imagine the Singapore airport will have these vehicles. Maybe you can put your luggage there and just bounce around, or you can walk. So among all the robotic applications, perhaps mobility is one that is closer to reality. So we're very excited about a lot of funding from the government to get this going. But of course, the ultimate goal is to have an arm on top of the vehicle doing something, like cleaning the roads, cutting bushes, or maybe make it smaller, serving us inside our home. Okay, so I'll stop here. I hope you enjoyed the presentation. This is work of the autonomous vehicle is funded by the Singapore MIT Alliance for Research and Technology. We started this work in 2010, and we're very happy with what we have achieved. Thank you very much.